Hi, thanks for coming to my talk. I'm Michelle, and today I'm going to talk to you about if anaerobic energy generation pathways are significant contributors to stream energy budgets. And before we get too far in, I should note that at the bottom of the slides, you'll see this QR code. It'll take you to the HTML web page for this project. So really, when we're thinking about energy metabolism, we're thinking about the balance between energy storage processes and energy releasing processes. And generally, we're just considering the aerobic process of gross primary production, or GPP, and ecosystem respiration, or ER. However, we know that anaerobic processes, such as denitrification, are common in streams. So this figure on your left here is from the LINXII project, where they studied denitrification rates across the US and found that rates were common. They could be high in some streams. And also we know from energetics that there's really only a 5% difference in the amount of energy that's released from ER as compared to the amount of Gibbs free energy that's released from denitrification. So then that leads us to this question of if anaerobic processes are significant contributors to overall stream energy budgets. So to investigate this, what we did was pull data collected by the LINXII project, and also we supplemented this with some data that was collected in our lab as part of a nationwide survey of denitrification and nitrogen fixation. So the LINXII datasets, they're all online. You can pull whole stream denitrification that was measured using a 15N tracer from the Mulholland et al. Supplemental. And also you can pull modeled metabolism from Bernot et al. Supplemental. So those links are there, and there's 48 streams across that whole survey. In our nationwide survey, there's 31 streams total. Here, I'm just going to present 7 streams to you because those are the 7 streams that we've been able to model metabolism in so far, but there's more coming. So we measured denitrification rates using chambers and amended acetylene inhibition assays. If you want more details on that, you should go ahead and see Amy Marcarelli's talk on Wednesday morning. And then we actually just pulled already modeled metabolism from the StreamPULSE repository. So to actually do this energy budget calculation, it's just really a unit conversion step. So here I'll walk you through this, but all of this is in more detail at that link at the bottom if you scan that QR code. So aerobic respiration, we have the equation there. What we do is we take the ER rate, we multiply that by the amount of Gibbs free energy, which is in kilocalories per electron in the balanced reaction. And then we multiply that by the number of electrons in the full reaction, and then we just convert the units of the ER rate. And so that ends up with an energy release from ER in kilocalories per meter squared per hour. And then we follow the very same approach with denitrification using the Gibbs free energy and the number of electrons in the balanced reaction. So then we're also interested in comparing how these energy generation numbers compare to the total energy released in these streams. So to do that, we're calculating a proportion of the total energy budget that comes from the energy released from denitrification by taking the energy released from denitrification and dividing that by the total energy released, which we've just calculated as the sum of the energy released from ER and the energy released from denitrification. And also what we've done is we've done some predictive modeling. So here we're interested in predicting the amount of energy that's released from denitrification as a proportion of the total energy. So to do that, we've first gone through all the pre-processing steps on these data sets. So that includes using dummy variables for categorical predictors, removing near zero variance predictors, and centering and scaling the data set. So for splitting the data set, we split it using a simple random split into 80% training and 20% testing. And then our resampling method here is using a 10-fold cross-validation repeated 10 times because these are both pretty small data sets. And then to evaluate the model performance, what we're going to do is choose the best fit model based on the lowest root mean square error on the testing set. So once we did our pre-processing steps, we found the Marcarelli nationwide data set was small. It had about 17 observations and 24 predictors. So I'm not going to show you the results from that data set model today because I'm worried about it being overfit. So I'm going to wait and hold off on that until we have the rest of the metabolism modeled to show you the predictive modeling results. But I'll go ahead and show you some of the energy budgets for that data set. But we can show you the LINXII dataset predictive model that had about 28 observations and 28 predictors. Some of those include the state where the rates were measured, land use, biome, discharge, reach width, and nutrients in the water. And because this session is focused on learning and hopefully learning new techniques, I just wanted to plug, I found the applied predictive modeling text very helpful, so I definitely recommend that. We're going to look at the LINXII results first, and I want to walk you through how I'm going to display these to you. So here you'll see this graph, and on the x-axis we have denitrification rate, and on the y-axis we're going to have energy released from denitrification as a proportion of the total energy budget. So then we have a one-to-one line there in the middle, that dashed line, which is going to signify that we have an energy contribution that's proportional to the rate. If we have deviations from that line, if it's below the line in that red triangle there, our energy contribution is less than we would expect given the denitrification rate. And then if we have above the dotted line in the blue, we're going to have an energy contribution that's greater than the expected based on the denitrification rate. So here we're seeing that we have denitrification rates that are contributing, that are higher here, but they're actually contributing less to the total energy budget than we would expect. And then in the inverse, we have denitrification rates that are low compared to the rest of the rates measured. These are on the low end, but they're actually contributing more to the total energy budget in those streams. So the takeaway here is a little weird. We have streams that have low denitrification rates, but in these streams, they could potentially be still depending on the amount of energy that's generated through denitrification, where in these streams that have high denitrification rates, they may not be depending on that energy generated, even though those rates are high. So let's take a look at the predictive model for these LINXII data sets and see if there's anything interesting we can pull out here. So we have our models that we've tried here in this column, and then we have the root mean squared error on the testing set, and we've chosen the Mars model here because it has the lowest root mean squared error on the testing set. That was our best fit model. And then on the right, we have, usually I would show you the top 5 most important predictors or the top 10 most important predictors. But in this Mars model, the best fit model only weighted 2 predictors as the most important. So that's what I'm showing you here, is that the most important predictor is nitrate, and then the second most important predictor is the percent of urban cover in the watershed. And so our takeaway here is that the nitrate is the most important factor in controlling energy production from denitrification. And this isn't like mind-blowing, especially in comparison to the original LINXII study, which was showing the nitrate was one of the most important predictors for actual denitrification rate. So this doesn't necessarily shed any new light on that problem of mismatch between energy budget and denitrification rate. So let's take a look at the chamber studies to see if we can parse this out. So this is the Marcarelli nationwide chamber denitrification rates. I'm showing you here amended denitrification rates versus that energy released from denitrification as a proportion of the total energy budget again. And we can see, so first I should say that because these are chamber rates, they're automatically not going to be directly proportional to the percent they give to the total energy budget, because in an ideal world, I would be displaying you multiple different types of substrates and then scaling that up to the whole stream in order to make these rates directly comparable. But I think this still gives us a good like ballpark of the dynamics here. So what we're seeing is these few chambers here have really high denitrification rates. But there's a huge deficit between those high rates and then what we would expect those rates to contribute to the energy budget. So again, we're seeing that mismatch, and the sediment rates, which are purple here, were some of the highest in the study. But again, they're kind of contributing, at least the couple samples that we have here that I can show you, are contributing less than we would expect to the total energy budget in these streams. Yeah, so that's a little weird too. And I want to explore this more. I think this is really interesting. And I want to understand why this is happening. So some further directions here. So first I have to tackle modeling the metabolism for the rest of the Marcarelli nationwide streams. That's 24 more streams here in red. So also that'll give us a better perspective on different ecoregions across the US and fill in some of the gaps that we have across different ecoregions in this study. And then after that, I have to scale these chamber rates. We can use some of the samples were collected at neon sites, about 14. We had about 14 neon sites in the nationwide survey. So we can use the neon stream morphology data products to then scale those chamber rates to whole stream estimates. So after we do that, I'd like to explore more of these factors that are impacting the energy production from denitrification. And I'm hoping that detailed data about different substrates can help us pull out what's really happening here. So I'd just like to thank everyone who helped put together these nationwide data sets. I'd also like to thank NEON, for specifically Kaylin Colley, Kelly Goodman, and Bobby Hensley for their help with metabolism modeling and NEON sites. Also, I have to plug this MIMSy package. If you work with MIMS data, maybe check it out. Thanks for checking out my talk. See you.